Greetings and welcome back. In this video we're going to be looking at a slightly different version of the Friedel-Crafts alkylation reaction. This one is called Friedel-Crafts Acylation. Instead of adding on an alkyl group, it adds on an acyl group. So an acyl group looks like this. This part right here is called an acyl group. It's essentially what is usually kind of determined to be part of a ketone. But it doesn't matter what's over on this side. It could be an oxygen, etc., whatever. But this is an acyl group. So if we add on an acyl group to a benzene ring, this is again another version of electrophilic aromatic substitution. We would start with a hydrogen somewhere, and we would substitute it for an acyl group, or a C double bond O R. So this is the R group we're adding on. The reaction is almost identical to Friedel-Crafts alkylation, but instead of adding on an alkyl group, we add on an acyl group and make a ketone. So let's start with a benzene and look at the way that this works. In fact, we add on the exact same things as before, which would be something with a halogen, usually we use a chlorine, and AlCl3. Once again, the purpose of the AlCl3 is that it makes that chlorine leave much better. So we would see this thing happen, and the chlorine would leave. That would give us something that looks like this. Double bond O with a C+, right? And that's what we saw for Friedel-Crafts alkylation. The difference here is that that's just not a carbon with a CH2 or something like that. It's a carbon in a carbonyl that has a plus charge. Well, there's a really good resonance structure of this, which would stabilize that plus by filling its octet, which would look like this. The resonance structure would have a C triple bond O, and in that case, the oxygen would be positively charged. So the structure on the right would be better than the structure on the left, but if you look at the reactivity, definitely this carbon with a plus charge and not a full octet would be an electrophile. If you look at the one on the right, the oxygen has the plus charge, but it has a full octet. So essentially this guy would want to pull electrons back towards itself, meaning it would want to steal some of these electrons, meaning that that carbon is fixing to lose some, so that carbon is once again the electrophile. So in either of these cases, that carbon is a really strong electrophile, so the mechanism of this reaction would be that the benzene ring, which I'll just redraw it again down here, the benzene ring's electrons would attack that carbon, or you could also say it could attack this carbon and kick those over. You would get the same answer either way, that we would have that new double bond, or sorry, that bond that was there, making a new bond to a carbon in a carbonyl. Nothing else gets kicked off. You would still have the H there, and you would still have an H up here, and we would once again get that positively charged carbocation intermediate, the AlCl4, which we created when AlCl stole that chlorine away, would once again use those electrons to grab that hydrogen. We would regenerate our benzene ring, and just like that, we would have done another version of electrophilic aromatic substitution, where we have now, instead of a chlorine or a bromine or something like that, we have added on an acyl group in exchange for the hydrogen. And that is Friedel-Crafts acylation. So instead of adding on an alkyl, we can add on an acyl, which is just a carbonyl followed by some R group. So you may remember that we had a good amount of limitations for Friedel-Crafts alkylation. Let's look at the limitations for Friedel-Crafts acylation. All right, number one stays intact. The first limitation for Friedel-Crafts alkylation is that it does not work with a deactivated aromatic ring. And that holds true for this reaction as well. So for instance, if you had a carbonyl on there, or you had a nitrile, or even a halogen, Friedel-Crafts acylation would not work as well. All right, and that's the only limitation. The second limitation for Friedel-Crafts alkylation was rearrangement. Rearrangement of that carbocation. So let's look. In this case, the carbocation that you get is not going to just be a normal carbocation. It's a carbocation that's part of a carbonyl. Because this guy has resonance, where it can fill that carbon's octet, then this actually becomes a relatively stable carbon. And due to that resonance, the carbocation will never rearrange, so this is not a limitation and not anything we need to worry about. The third limitation for Friedel-Crafts alkylation was that the product would often react again. So let's look at that one in this case. Alright, so in Friedel-Crafts acylation, we start with a benzene ring and we turn it into, well, let's just put on a little acetyl group, so just the C double bond OCH3. Well, remember that the carbonyl being directly attached is actually deactivating. Therefore, this guy is still reactive for electrophilic aromatic substitution. Because of rule number 1, this is deactivated, the product. And deactivated means that it will not react again. So, it will not react again. We never have to worry about that. And Friedel-Crafts acylation will only happen once. You will never end up with any di or tri-substituted products. So it's really neat with Friedel-Crafts acylation. These same guys went back to work, and essentially what they found out is a way to be able to do to fix most of the problems with Friedel-Crafts alkylation. You can do acylation, not have to worry about rearrangement, not have to worry about it reacting again to give you a di or a tri-substituted product. So in essence, Friedel-Crafts acylation is a much better reaction than Friedel-Crafts alkylation. You might ask though, first off, why would we want to even talk about Friedel-Crafts alkylation? Well, Friedel-Crafts acylation only puts on an acyl group, it never puts on an alkyl group. But then, why would Friedel-Crafts acylation be any good? Well, it's good if you want to put on an acyl group. It's also good because we can turn that acyl group into an alkyl group if we want to. So let's look at, for instance, a butyl. So we will put on a 4-carbon chain that is an acyl group. If you look back to our limitations of Friedel-Crafts alkylation in the last video, you may see that I tried to put on a 4-carbon chain, but it didn't work, it rearranged. If in this case we put on that group, well, it still wouldn't be a nice straight 4-carbon chain because we would have a carbonyl there. So it would be a C double bond O followed by those 3 carbons. So it's not quite what we were looking for, but we have a reaction called the Clemmensen Reduction, in which we can add zinc, usually with a little bit of mercury in there as well. It's kind of doped with mercury, and some HCl. Metals tend to give off electrons, and of course in this place we have plenty of H pluses. So what this reaction will let us do, the zinc provides the electrons, the HCl provides the H's, and what it will allow us to do is to turn that carbonyl into a CH2. We'll reduce it all the way down to a CH2, and therefore we can get that 4-carbon chain. And this would be by doing Friedel-Crafts acylation, followed by a reduction of that carbonyl, and this is called the Clemmensen Reduction reaction. The Clemmensen reduction will work for any carbonyl, work for any ketone or aldehyde, but It's especially important when we're talking about Friedel-Crafts acylation because it lets us go from a benzene ring to an alkyl chain, so kind of an alkyl benzene, which at first glance looks like Friedel-Crafts alkylation would work best. But if you go through Friedel-Crafts acylation and then reduce it afterwards, you don't have to worry about that second or that third limitation. We wouldn't end up with a whole bunch of multi-substituted products. So we wouldn't get a bunch of this. And we also wouldn't have to worry about rearrangement. So if you did this by Friedel-Crafts alkylation, we would actually end up with this thing, which is nice, but not necessarily what we wanted. If you go through Friedel-Crafts acylation followed by reduction, you get the only product that you want. So that's part of why Friedel-Crafts alkylation is a pretty well used reaction, especially coupled with the Clemmensen reduction. Thank you very much, and I will see you in class.